This is video number 85 in our series on tensor calculus. In this video, we're going to extend our analysis of the commutative operator to all vector forms, scalar functions, and tensors of higher rank. In video 82, we introduced the Riemann tensor here by applying the commutative operator to a contravariant vector component. Well, today what we want to do is to see what happens when we apply this same operation to other forms of vectors, scalar functions, and tensors of higher rank. So first of all, let's ask ourselves the question, what happens if we apply this commutative operator to a covariant vector component? Well, we could go through the same exercise we went through on video number 82, expand it all out, we'd get the right answer. But we don't need to go through all of that. What we'll do is simply to lower this index into the lower position. And of course, you know how to lower an index. What we do is to multiply both sides by the covariant metric tensor. So what I've done is I've renamed lambda to sigma, and then I've multiplied both sides of our equation here by the covariant metric tensor. I've also expanded out the commutative operator in this form because it's a little easier to understand what we're going to do. You'll remember that our covariant metric tensor is metronylic with respect to the covariant derivative. That means that it works its way across all of these operations and affects this target object over here. We can lower the index all the way across these operations. On this side, the operation is just to pull this index down into this position, making it lambda. Now what we'll do is to switch these indexes, and you know from the previous video that when we do that we have to change the sign because the Riemann tensor is antisymmetric with respect to these two indexes. So this will become a negative r omega lambda alpha beta times our contravariant vector component right here. So finally what we're going to do is to flip-flop these two indexes. This is a dummy index, so we can always raise one and lower the other one at the same time. And that's going to give us the end result that we're looking for. So now let's compare this result with this one. Here we have the index in the upper position, here it's in the lower position. We have the Riemann tensor in both cases, but here we've got a positive expression, here it's negative. Here the contraction is between these two indexes like this, and here it's between the two indexes this way. So the expressions are very similar. It's just that this one is negative and the contraction goes from high to low instead of low to high. It's really that easy. Okay, let's move on now and see what happens when we apply the commutative operator to a scalar function. So our goal is to apply this commutative operator to this scalar function. Well, let's go through the process that we went through in video number 82. First thing we're going to have to do is to find the covariant derivative with respect to beta of our object f. And of course, for a scalar function, you know that's simply the partial derivative. So this is the partial derivative of f with respect to s beta. Next step is to find the covariant derivative of that with respect to alpha. Okay, well, first step is always to find the partial derivative, and that makes this a second partial of f with respect first to beta and then alpha. Well, this object up here has become a covariant vector component. Started out as a scalar function, but this operation added a lower index and makes it a tensor of rank 1, a covariant tensor of rank 1. So to complete this, we need a negative term, because the index is in the lower position, of gamma, and the indexes here are alpha and beta, and a dummy index that is going to form a contraction with the partial of f with respect to s omega. So this is the full operation of the covariant derivative with respect to alpha of the covariant derivative with respect to beta of f. This is the full expression. So now what we have to do is to find the operation in the opposite order, and that means we just copy this, renaming alpha to beta and beta to alpha. Finally, we add this term and subtract this term to get our final result. Well, in the process, these two cancel. The order of differentiation doesn't matter, so these are the same term. Likewise, the order of these indexes does not matter, and that means that these two terms cancel. So the end result is everything cancels out, and the result is simply equal to 0. So the commutative operator applied to a scalar function is simply 0. The operation commutes with respect to a scalar function. Now this is also true for any invariant object, such as a straight vector like this, or any form of a full contraction such as this. So whenever we have any expression that has no free indexes, the commutative operator applied to that function is going to be equal to 0. So given this result, let's move on and see what happens when we apply the commutative operator to a vector with an ambient index. Well, now that we know this is true, that is the commutative operator applied to an invariant object like this vector here, now that we know that that's equal to 0, let's expand this out, expressing our vector t as a linear combination with an ambient index. So here, this operator is the same as this, and we've expressed this vector as a linear combination, ti times zi. All right, well, the key to this is the fact that we'll recall that our ambient basis vector here is metronylic with respect to the covariant derivative. That is that this basis vector can work its way across each of these operations unaltered. So we can take zi out across this operation and then out across this one and all the way out of the operation itself. In other words, we can express this in the following form. So what we're saying is that the commutative operator applied to this linear combination will give us the same result if we apply the operation just to the vector component and then multiply that result by the basis vector. We can pull this basis vector all the way out of the operation. Well, because we now know that this whole thing, because of this, is equal to 0, then that means that since this factor is not equal to 0, that means that this factor itself must be equal to 0. And because we can flip the position of these indexes, raise one and lower the other, then it should immediately be obvious that the same analysis works for an ambient index that's in the lower position. So what we've discovered is that the covariant derivative commutes with respect to a scalar function or any other invariant expression. It also commutes for a vector that is expressed in terms of an ambient index. It's only when the vector is expressed in terms of a surface index that the covariant derivative does not commute, and we have to make use of our Riemann tensor to express the result. Okay, well, let's move on and explore a couple of additional properties of the commutative operation. Let's see if our commutative operator obeys the sum rule. Well, we'll go through the normal drill here. We'll start with the covariant derivative with respect to beta, and of course we know that the sum rule works for that. Now we'll apply the covariant derivative with respect to alpha. Next, we copy this expression, switching alpha and beta. Finally, we're going to add this expression and subtract this expression. Now, as we do that, it's pretty obvious that these two terms together, taking this one and subtracting that one, is going to give us 3 times the commutative operator of s omega I lambda j. And likewise, this term minus this term is going to give us 5 times the commutative operator of t omega I lambda j. So with that, it's very clear that our commutative operator here applied to a sum of terms will be the same if we apply the operation to each term separately, and of course we can bring out the scalar factors here. Now we've done it for a specific example, but of course it's very obvious that it is generally true. It would work for any case where the indexes are consistent here. So it would work for more than 2 terms added together, and it works for any ranked tensor whatsoever. Now this was a pretty trivial exercise. It's something we probably could have done simply by inspection. But let's move on now and see what happens when we try the product rule. All right, we'll use this example and go through the same exercise. But this time, as we apply the covariant derivative with respect to beta, we of course have to use the covariant derivative product rule. Now, as we apply the covariant derivative with respect to alpha, we're going to have to apply the product rule to each of these terms. Each of these are products themselves, so we have to apply the product rule to each of these. We're going to wind up with 4 terms altogether. All right, make sure you see it. When we take the covariant derivative of this term with respect to alpha, we first have to apply it to this factor, giving us this, holding the second one as it is, and then over here we hold the first factor as it is and apply the covariant derivative with respect to alpha of the second term. So together these 2 terms represent the covariant derivative with respect to alpha of this one term. Likewise, these 2 are the covariant derivative with respect to alpha of this term over here. Okay, so the next step is to copy this last expression, switching alpha and beta. Finally, we will add this expression, and we will subtract this expression. All right, in the process, we'll see that some things will cancel out here. This term is identical to this one, so they'll cancel each other out. And this one are identical, so they disappear. And we're left with only 4 non-zero terms here. Now, if you look at these 2 guys together, you'll see they both have a common factor of ti lambda. And these 2 guys, this one and this one, when we subtract this from this, it's obviously the commutative operation applied to s omega j. Likewise, if we look at these 2 terms, we see that there's a common factor of s omega j, and this term minus this one gives us the commutative operation applied to ti lambda. So in the end, it's very clear that our commutative operator here does in fact obey the product rule. If we apply this operation to a product of terms, it's the same as applying it first to the first factor times the second factor unchanged, and then the first factor unchanged times the commutative operation of the second factor. Now, again, we've used a specific example here, but if you follow this through, you can see that it very clearly works in general. It doesn't matter what the rank of these 2 tensors happen to be. You're going to see these terms cancel out in the process, and this same expression will appear up here. And of course, it will apply if we have more than 2 factors. So everything we've said about the product rule relative to the covariant derivative also applies to the commutative operator. Well, now that we know that the product rule works, Let's expand this expression out and see where it leads us. And of course, to do that, we need to use our commutative operator here and apply it to each one of the factors one at a time. So we're going to wind up with 4 terms over here. It'll look like this. What we've done here is to apply the operator to s omega in this factor, leaving the other 3 unchanged. Here we apply it to t lambda, here to ui, and here to vj. Okay, but if you remember a few minutes ago, we discovered that applying our commutative operator to a vector component with an ambient index gives us a result of 0. So this term and this term are both 0. So the entire terms drop out of the expression. So expanding this out gives us only 2 terms right here. And of course, in both of these cases, we know how to represent these operations as a contraction using our Riemann tensor. So let's work out the expression in those terms. Okay, be sure you see what we've got here. What we've done is to form a contraction right here that is the equivalent of this factor. We formed a contraction here with this one and the negative sign, which is the equivalent of this factor right here. And of course we have ignored these 2, as we said, because those results are going to be 0. So this general result gives us the rules that we need in order to apply the commutative operator to any list of factors like this. So here's the pattern. We walk through every one of the factors in our expression and we look for the surface indexes. We're not interested in the ambient indexes. We can ignore those. So for each surface index that's in the upper position, we form a contraction from high to low in this direction, and it's a positive term. For each index that's in the lower position, like this one, we form a contraction that goes from low to high here, and it's a negative term. So each lower index gives us a negative term with the contraction going this way. Each upper index gives us a positive term with the contraction going in this direction. And again, we can ignore any of them that are ambient indexes. Now, while we're here, let's check to see what happens if we form a contraction. What if we rename lambda to omega here? Let's go through and do that. Lambda is replaced with omega. Well, if you look at it, if we rename omega to sigma and sigma to omega, then these 2 terms are now exactly equal. And one's positive, one's negative, so both of these cancel each other out, leaving the total result to be 0. And that's exactly what we would expect, because this contraction here is basically a contraction that forms a scalar function, and we can ignore that in our operation, and we can ignore any factors that are ambient indexes. So this gives us a result of 0, which is exactly what we'd expect. So not only do we look for only surface indexes, but we're only interested in surface-free indexes. All the other cases can be ignored. All right, now finally this leads us to the general result for a tensor of any rank, and it looks like this. The rules for expanding this expression out are exactly the same as they were for this expression up here. What we do is to look at each of the indexes one at a time, and we're only interested in free indexes, and we're also only interested in surface indexes. So for each free surface index, we're going to need a term. If the free surface index is in the upper position, it'll be a positive term, and the contraction will be formed in this direction. For each free surface index in the lower position, we'll have a negative term, and the contraction will go in this direction. Exactly the same rules as we had up here. Now, I'm not going to take the time to prove that this is so. What I'm going to do is to refer you back to video number 35. That's where we discovered that if we knew the rules for a set of factors with indexes, then the corresponding expression where all of the indexes were in a single tensor was exactly identical. And the proof that we used in video 35 is the same one you can use here. So go back to 35 and look what we did there, and you'll easily be able to prove that knowing this is true gives us the knowledge that this is true as well. Okay, so we've covered a lot of ground here. Let's finish up by doing a quick recap of what we've accomplished. We started with this expression, which is what we derived back in video number 82. You'll remember there that we said when we apply the commutative operator to a vector component that has a surface index in the upper position, we simply formed this contraction with the Riemann tensor. Well, based on this result, we were quickly able to show that this is the form needed if the index is in the lower position. The difference is that the term is a negative term and the contraction is formed in this direction instead of this direction. Well, we then went on to explore what happens when we apply the operator to a scalar function. We found the result is 0. We found the same to be true if we apply the operator to a vector that has an ambient index in either the upper or lower positions. So the bottom line is this, that the covariant derivative actually commutes in every case except when we have a surface index in either the upper or lower position. And depending on which case we have, we'll use either this form or this form. We then went on to explore a couple of general properties of the commutative operator, and we discovered that the commutative operator obeys both the sum rule and the product rule, and these take exactly the same form as they do for the covariant derivative itself. Applying the operation to a sum of terms is the equivalent of applying that operation to each term separately and then adding the results. And of course we can bring out the scalar factor here. Concerning the product rule, again, this is exactly the same form as with the covariant derivative. If we apply the operation to a product of terms, it's the equivalent of applying the operation to each factor separately, keeping the other factor constant in each case, and adding the results together. Works exactly like it does for the covariant derivative itself. And finally, based on all of these results, we were able to come up with a general pattern for applying the commutative operator to tensor expressions of any rank. So what we do is to look at the expression and pick out any surface indexes that are free indexes. We can ignore anything else. For each free surface index in the upper position, we add a positive term that has a contraction in this direction. For every free surface index in the lower position, we include a negative term with a contraction in this direction. And by following that pattern and technique throughout, we're able to apply the commutative operator to tensors and expressions of any rank.